If you're like most people, then when I say a mathy kind of word like equation, you probably have an immediate gut reaction. You might have a vague sense that I'm asking you to do something, even though all I did was say a word. Maybe you get flashbacks to sitting in algebra class, moving terms around, and solving the quadratic formula without ever being told why you were doing any of it. But maybe the reason people feel this way isn't because math is hard, or even that it isn't practical. Maybe it's that if you grow up only seeing equations and other math ideas while you're being asked to solve problems, then you end up thinking that math is all about solving problems. And to me, that completely misses the bigger picture. Really, math is less about calculating numbers or solving for x, and it's more about describing patterns and relationships. It's just that the symbols we use in math, like equals and x and plus, look a little different from what we're used to in daily life. But those symbols are all just shorthand for ideas, and you can explain any of those same ideas in English if you wanted to. There is no such thing as a math-only idea. It's all just regular old ideas. So in this video, I'm going to present some different ways of thinking about variables and equations. I'm going to make the case that at their core, variables just represent the idea of any number, and that equations are just one way to describe relationships between numbers. That's it. To say that another way, if you have any two things that can be represented as numbers, and you want to know what you can say about how those two things are related, then you can probably describe that relationship using variables and equations. Lastly, I want to try and give you some visual intuition for equations and what they're doing in a geometric sense. After all, numbers are very geometric things. They can be big or small, you can stretch them and move them around, just like shapes and stuff and everything else that lives in some kind of space. And since equations are all about numbers, the ideas that they represent can also be pictured as happening in space. Alright, if we have to talk about numbers, then let's start with something familiar, the number line. Now you can think of it as the space where numbers live. We can draw tick marks for the integers, but it's implied that all of the numbers in between, like 1/2 and the square root of 2 and pi, are also in there somewhere. So every point on the number line represents a different number, including the points that aren't on a tick mark. So what do we know about numbers? Well, in plain English, a number is used to describe an amount, like money or volume or cups of soup. And the thing that makes amounts useful is that we can compare amounts to each other. Any amount is always more than, less than, or equal to any other amount. Let's actually pause on that last sentence. Without actually mentioning any specific numbers, we said an idea that we can write down using equations. What we said was, if we have some amount, meaning some number, and we also have some other number, then we know that one of three things must be true. Either the first number is less than the second number, or the first number is equal to the second number, or the first number is greater than the second number. If we pick two specific numbers, then only one of these equations can be true at a time, since you can't have a number be both bigger than and smaller than some other number. But if we don't pick specific numbers, then all three equations might possibly be true, and that's why we wrote down these ors in between them, so that the conditional relationship between these equations is clear. Note that these equations aren't something that we made up, and are not problems to be solved. They're just representing a fact about how numbers work. In fact, we already wrote down the same thing in English right here. So in this case, these equations aren't adding any information, they're just stating this idea in a different, more mathematical looking way. Okay, let's get back to the number line. Now when you actually look at a number line, most people don't have a problem with the idea that all of the numbers on it just exist at the same time. Technically, there are an infinite number of numbers being shown here. That's not really a problem because, well, that's what a line is. It's just an infinite number of points arranged one after the other. If you want to pick an individual number, all you have to do is draw a dot somewhere on the line and move it left or right until you get to the number you want. But for whatever reason, when we start talking about variables like x, people feel an instinctive need to choose one specific number. And when people see x getting used in equations and multiplied and added to as though it is a specific number without actually choosing one, that can feel uncomfortable, like we're cheating somehow. I think this happens because when people are first introduced to variables in math, they're often explained as a number that we don't know the value of yet. And that makes it seem like the variable x is a problem that's waiting to be solved. Or worse, it sounds like the teacher knows what x is, but the students don't. But it's actually just the opposite. Not having a specific value for x isn't a problem at all. In fact, that delayed choice is exactly what makes variables so powerful. It's not that we don't know what x is, it's that we do know that x could be anything. So, instead of thinking of x as a spooky mystery number, try thinking about x as representing the entire number line all at once. All of those points on the line aren't waiting for you to choose one of them. They're all just options. They're all equally valid. In some sense, a variable like x is literally a space of possibilities. The reason this is so powerful is that you can still treat x as though it were just a number. You can multiply it, add it, and all the other number stuff, and everything still just works. You get all the benefits of a number, just without the commitment of actually choosing a number. Okay, that's cool and all, but variables wouldn't be very useful if you couldn't choose a specific number for them. I mean, if we wanted to point to some random number and say, I'm going to call this one x, there's no reason we couldn't do that. So, if we're trying to picture numbers geometrically, then what does choosing a value for x look like visually? Let's say we want x to be equal to 4. Well, we can visualize this by drawing a dot at 4 on the number line and blurring out the rest of the line. As an equation, we'd write this as x equals 4. Now, it's important to note that this equation, x equals 4, is something that we chose. It's not an answer that we got by doing math. It's just a random decision that we made up, and it only applies to this made up scenario that we're talking about right now. You can think of this equation, x equals 4, as saying, pretend there's a number called x, and that number has a value of 4. If we want to make it extra clear that this is something we decided, we can write let x equal 4, where let basically just means just go with it for now. Okay, now we have one equation, and we have one point on our number line. So one way you can think about equations in general is that they're choosing a set of points on the number line. Or in other words, equations are like filters that take in all of the possible points and spit out only the ones that pass their test. If an equation is true for a given point, then that point passes the test and you keep it. If that equation is false, then that point gets thrown out instead. In this example, we happen to be choosing just one point, but really you can choose as many points as you want to. For an example where we choose 2 points, let's instead look at the equation x equals x times x, and we'll throw out x equals 4, since we're talking about a different scenario now. If we try our old value of x equals 4 with this new equation, we see that it doesn't actually hold up, since 4 does not equal 4 times 4. But it turns out there are two values of x that do work with this new equation. X can be 0, since 0 equals 0 times 0, or x can be 1, since 1 equals 1 times 1. And don't worry too much about how we found those two values. All you need to know for now is that this equation has two separate solutions, or two different points that pass through the filter. So to represent this equation visually, we can draw two dots on the number line, one dot at 0 and another dot at 1. Now if we stop worrying about the equation for a second, and we just look at the dots on the number line, we can see that if we wanted to pick a value for x, it would have to be either 0 or 1. More formally, we can write this as x equals 0 or x equals 1. And the specific way that we wrote this is important. It's not that x is 0 and 1 at the same time, it's that x is allowed to be either 0 or 1, and both options are equally valid. That means if we want to use these two equations to describe this constraint without using the original equation, we can't just choose one equation and throw out the other. We have to use both, and we need to keep the or in between them to explain the way that they're working together. Let's take a step back now. We started with a single equation, x equals x times x, and now we have three equations. So what actually happened? We didn't add any new requirements. All we did was figure out what values of x work with our original equation. Well, it turns out that what we just ended up with is a different representation of the same logical constraint that our original equation gave us. The actual constraint we're dealing with is just x is either 0 or 1. And you can visualize that constraint without using any equations, just by drawing two dots on the number line. So really, these two dots, and this sentence, and this equation, and these two combined equations are all just different ways of saying the same thing. Okay, so If we can combine equations together using OR, then it's reasonable to think that we can also use AND. So what does that look like? It's a little easier to picture how it works if we use regions of space, or line segments, instead of just individual points. So let's define two inequalities, or two constraints, x is greater than 2 and x is less than 3. Visually, we can represent x is greater than 2 as all the points to the right of 2, and x is less than 3 as all the points to the left of 3. We use these little round parts to show that 2 and 3 are not included. Now, try to forget about all the math stuff for a second. In plain English, if x is greater than 2 and x is also less than 3, then we know that x must be somewhere in between 2 and 3. And we can show that on the number line by shading in the region between 2 and 3. And this is exactly the same region where the points on our first two number lines overlap. If you study logic, this is called the intersection, because it's where the two things bump into each other or intersect. And it turns out this works for any two equations that are both true. That is, any two equations that have an and between them. All you have to do is keep the points that overlap and throw out all the points that don't. Now, if you really think about this for a minute, it should be kind of obvious that you can mix and match equations like this. After all, equations aren't some kind of magical math machines with made-up rules. They're just statements that you could say in English if you wanted to. And anytime you have any two statements that are either true or false, you can just use logic to talk about them. And since you can use a Venn diagram to represent logic, you can also use a Venn diagram to figure out what happens when one, or the other, or both, or neither, or either of these equations are true. It's more than a coincidence that the space that we're working in, the number line, looks pretty similar to the space that a Venn diagram lives in. And that's what allows us to visualize equations overlapping in this nice way. In fact, if you were to look at 2D space, and you found the equation for this region of space, and you found the equation for this other region of space, then the way that you would combine those equations using and OR would literally just be a Venn diagram. So the lesson here is, if you can come up with a visual way to represent the thing you're talking about, there's a good chance that the picture itself will tell you something that wasn't obvious before. The reason is that anything that lives in any kind of space has to play by the rules of that space. And since spaces are described using numbers, granted with a few extra rules, that means that whatever thing you're picturing also has to play by the same rules that numbers play by. So the next time you're looking at an equation, instead of immediately trying to solve it or see it as a problem, try asking yourself, what is the space of possibilities, and how does this equation limit that space? If the equation only has one variable, like x, then you can think of x as just being the number line, and the equation as a constraint that makes that space smaller. When you start using two or more variables, you can still think of it in terms of spaces, you just start using higher dimensional shapes and graphs. And that's exactly what we'll be covering in the next video. So if you enjoyed this video and want to see more content on how to think about math, consider subscribing or giving a like so I can see whether I'm on the right track. I'd also love to hear in the comment section if you have a different way of thinking about variables and equations. One of the coolest things about math is that there are so many ways to think about it, and each way tells you something new. Sharing those ideas is a great way to test your own understanding and help others learn.